Today we'll learn how to construct bending moment diagrams by principle of superposition. We have already known the content of superposition principle. That's for structures with linearly elastic materials. If a structure is linearly elastic, the forces acting on the structure may be separated or divided into any convenient fashion, and the structure may be analyzed for the separated cases. The final results can then be obtained by adding up the individual results.
Look at them by using superposition method. The simply supported beam subjects to uniformly distributed load Q and two end couples MA and MB. The structure can be divided into two cases according to the principle of superposition. One is the structure under the action of two end couples. The other is the structure subjected to uniformly distributed loads. Look at this case. According to what we learned last time, by using the relationship of external loads and internal forces, Q is equal to 0. So for this case, the bending moment diagram is a straight line. At the end here, M is equal to MA, lower side in tension. At this section, the M is equal to MB, upper side in tension. So we could construct the bending moment diagram. For the second case, a simply supported beam under the action of uniformly distributed load Q, the bending moment diagram is a 2-degree parabola. Then by using superposition method, the original structure's bending moment is equal to M1 plus M2. When we draw the bending moment diagram for the original structure, usually we draw the straight line as a dashed line and take this dashed line as a baseline to superimpose such a parabola. This is the bending moment diagram for the original structure. When construct the bending moment diagram, pay attention that we usually superimpose the ordinates, not the figure. The ordinates are perpendicular to the beam, not to the dashed line. For example, here, when we superimpose this QL squared over 8, the ordinate is perpendicular to the member AB, not to the dashed line. Example 2. This beam is subjected to FP, Q, and M. When construct its bending moment diagram, we usually divide the beam into several parts to use superposition method segment by segment. Firstly, let's construct bending moment diagram of part CD. We take CD part as a free body to draw the free body diagram. For the section C, the shear force is FQC, the bending moment is MC. For the section D, the shear force is FQD, bending moment is MD. For a simply supported beam, if it has the same length with the CD part and subjected to same load Q, MC and MD at the two ends, whether the internal forces of any section are same for these two cases. For the first case, let's calculate FQC and FQD. According to equilibrium condition, sigma MD is equal to 0. We could establish that FQC times L minus QL times half of L plus MC is equal to MD. Then we could solve that FQC is equal to negative MC plus MD over L plus half of QL. According to sigma Fy is equal to 0, then we could solve FQD is equal to negative MC plus MD over L minus half of QL. For the simply supported beam, we could also solve its reaction YC and YD by using equilibrium condition. YC is equal to negative MC plus MD over L plus half of QL. That's equal to FQC. We could also solve YD is equal to MC minus MD over L plus half of QL. And we find that actually YD is equal to negative FQD. Then we find that these two cases have the same bending moment diagrams, but the deformation of the two cases are different. Now let's look at the original structure. If we divide it into three parts, AC part, CD part, and DB part, we could draw the free body diagram for each part. The CD part's free body diagram, the AC part's free body diagram, and the DB part's free body diagram. These three parts are equivalent to simply supported beams separately according to what we discussed just now. So CD part could be represented by this kind of simply supported beam under the action of Q and the two end couples MC and MD. AC part could be represented by such a simply supported beam under the action of FP and an end couple MC. DB part could be represented by such a simply supported beam under the action of M and MD. Then we could draw the bending moment diagram for each part using superposition method. For AC part, because section C has a capital MC acting on it, so its M is equal to MC, lower side in tension. So we connect section C's MC with section A's 0 by such a dashed line, then superimpose such a fold line. And this value is equal to a quarter of FP times LAC. For the CD part, we could draw its bending moment diagram by using superposition method. Section C's M is equal to MC, lower side in tension. Section D's M is equal to MD, lower side in tension. So we connect these two sections by a dashed line, then superimpose such a parabola. And this value here is equal to Q LCD squared over 8. For the DB part, we could draw its bending moment diagram. Section D's M is equal to MD, lower side in tension. We connect this section D with 0 here by a dashed line. Then take this dashed line as a baseline to superimpose such a fold line. So for the original structure, we could determine the control section's bending moment, such as MC and MD firstly. Then construct the bending moment diagrams of control sections by dashed lines. We suppose that MC and MD, the value here and here, both lower side in tension. Then for section A and section B, M is equal to 0. So we connect these four control sections M by dashed lines. Then for each part, superimpose fold line, parabola, and fold line. This is the bending moment diagram for the original structure by using superposition method, segment by segment. The steps of superposition method, segment by segment. The first step Usually, we divide the beam into several segments according to the loads applied on it. Determine the magnitudes of bending moment at control sections. The second step, draw a line as the axis and lay off the ordinates at control points on the tension side of the beam by magnitudes solved above. Then connect these points with dashed lines. The third step, take the dashed lines as baselines and superimpose the ordinates of bending moment diagrams for the corresponding simply supported beams, segment by segment. Now let's do some exercise to practice how to construct the bending moment diagrams by using superposition principle. Look at this overhanging beam under the action of uniformly distributed load and a couple. We could divide it into two parts. BC part can be considered as a cantilever beam. AB part can be considered as a simply supported beam under the action of an end couple MB and a couple at section D. So firstly, let's think about the construction of bending moment diagram for the BC part. We draw the axis of the member ABC. For BC part, under the action of uniformly distributed load, obviously the upper side in tension and the bending moment diagram is a parabola. Section B's M is equal to Q times L squared over 2, so that's 4 kilonewton meter. For section A, its M is equal to 0. So we could connect section A and section B's M by such a dashed line. Then take this dashed line as a baseline to superimpose AB part under the action of the couple at section D. For this dashed line here, this value at section D is 2. And then we superimpose for the left part, AD part, at section D's left side. The value is 4, so 2 plus 4. And for the section D's right side, the value is 2 minus 4, so that's 6 and 2.